Today's news is, honestly, about a technology that still looks nowhere near usable. And yet, the way I read it, this is one we can't ignore. Because it shows TSMC, the world's largest foundry, stepping in as a direct participant in research on materials beyond silicon. Today, I'll walk you through that delicate distance and why it matters.
Welcome to Semiconductor News Decoded. I'm Tai, with 31 years inside the semiconductor industry, bringing you the real view from the factory floor. Today, we're looking at a 2D semiconductor result announced by TSMC and a Taiwanese university. By the end, you'll know what 2D semiconductors are, what actually moved forward here, and why TSMC keeps funding research that still can't be used.
Here's today's news in one picture. Imagine a new kind of board, hyped for years as the building material of the future. Thinner than paper, yet strong, with a perfectly smooth surface. Build with it, and you get structures lighter and thinner than anything before. We'll lean on this board all the way through the opening section. But this board has an awkward property. The surface is so smooth that paint simply won't grip it. And you can't use a board outdoors without a protective coating. On an ordinary board, paint catches in the tiny roughness and sets. On this one, there's nothing to catch on at all. Craftsmen spent years trying to paint it. The coating came out blotchy or beaded up and slid off. Interesting material, they'd say, but you can't build a house with it. And so the board sat in the warehouse for a long time, treated like a prototype that never graduated. Then, one team of craftsmen found a new approach. Instead of painting directly, they first laid down a special primer, as thin as a breath, pressed tight against the surface, hardened it into a foundation, and only then applied the real coating. With that two-step method, a single sample board came out beautifully finished. But let's stay calm here. Finishing one sample board is a completely different problem from coating an entire building or a whole city to the same quality. Still, what you can't overlook is that the largest construction firm in the industry is running this research in its own lab. From here, let me walk you through what this actually looks like in the real semiconductor industry. Here's the news. TSMC, the world's largest foundry, and a research team at National Yang-Ming Chiao University in Taiwan have built a high-performance top-gate transistor using single-layer molybdenum disulfide, MOS2, as the channel. DIGITIMES reported it on August 6th, and the work is published in the journal Nature Electronics. Materials like MOS2 are called 2D materials. Even at a thickness of just a few atomic layers, they still work as semiconductors. That's why they've long been seen as a candidate channel material, the path the current flows through in a transistor, for the era beyond silicon scaling. In the analogy, this is the thin, glassy smooth board. The biggest challenge is the paint won't stick problem. The surface of a 2D material is flat at the atomic level, with almost no dangling bonds for chemistry to grab onto. That makes it hard to grow a uniform gate dielectric, which every transistor needs, and it invites interface defects and electron scattering. A beautiful surface as a material, a nightmare from a manufacturing point of view. That has been the bottleneck for years. In this work, the team grew an extremely thin layer of aluminum cleanly on top of the MOS2 under ultra-high vacuum, oxidized it into an aluminum oxide seed layer about 0.42 nanometers thick, and then deposited the real dielectric on top. The result? An EOT, the standard measure of how thin a dielectric behaves, of about 1 nanometer. On transistors with a channel length near 100 nanometers, the peak transconductance, a key performance metric, reached 0.45 millisiemens per micrometer. In other words, they got a thin dielectric and good current drive together, two things that usually trade off against each other. Now to the heart of it. My honest first reaction was, 2D materials? People are still working on that? This line of research has been around for years, and my view has been interesting science, but a long way from real chips. Looking at this result, that impression hasn't fundamentally changed. The reason is simple. This data is single transistor performance.
What matters in a semiconductor product isn't the one device that hit a record. It's whether hundreds of millions or tens of billions of identical devices all behave the same way. Threshold variation, contact resistance, leakage, drift with temperature, long-term reliability, and yield. There is wall after wall waiting down that road. On top of that, this MOS2 device is essentially an N-type transistor. Building logic requires P-type as well. Among 2D materials, WSE2 and others are being studied as candidates, but you'd need to make both stably on the same manufacturing platform, then step through inverters, circuits, and scale-up. This paper contains no circuit demonstration. As I read it, this is still device-level research. And yet, there's one reason this news is hard to ignore. TSMC. The paper lists TSMC's corporate research division as a collaborating institution, and Juliana Radu, who leads their advanced device research, is among the authors. The world's largest foundry is putting its own resources into 2D materials. That carries a slightly different weight than a university press release. At least it did for me. The other thing that caught my eye is the material itself. What they used wasn't the small, mechanically exfoliated flake you often see in the lab. It was single-layer MOS2 grown by CVD, a method suited to manufacturing. To me, that says the question has shifted from, can a 2D material make a transistor work, to how do we turn it into something a fab can handle? In semiconductor history, technologies dismissed as unusable for years have sometimes turned real the moment one problem broke open. High-K metal gate was like that. So was EUV. Both were carried through years of research full of problems, and they became today's manufacturing technology because somebody refused to quit. Of course, there's no guarantee 2D materials follow the same path. I think there's a very real chance something else beats them along the way. So here's where I land. My first reaction, still nowhere near usable, hasn't changed. This is nowhere close to the stage where you'd discuss production plans alongside today's GAA or CFET beyond it. But the one fact worth keeping in a corner of your mind is that TSMC itself has started engaging with the problems of manufacturing this. Don't expect too much, but don't forget it either. This is a piece of news to watch loosely, and that's about right. Let me sum up. TSMC and Ming Chiao Tung University improved the long-standing problem of the interface with the gate dielectric on a single-layer MOS2 transistor. But this is a single device result. Between here and volume production, walls remain. Variability, yield, and establishing P-type, to name a few. Even so, the substance of the research has clearly shifted from the physics of the material toward the problems of making it in a fab. And the world's largest foundry is involved as a direct participant. As a quiet piece of groundwork aimed beyond the limits of silicon scaling, let's keep watching this one together, loosely. That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Tai on Semiconductor News Decoded.